Friends, it's indeed a great privilege to be here on this occasion, the symposium organized to honor and recognize Professor Danny Shechtman for discovering the quasicrystals and for graciously aging to 70 years. And the privilege is all the more because we are celebrating with friends from across Israel, from across the globe. I first met Danny, he might not have known that, in print when his paper, 1984 paper, reached India in January 1985. At once I fell in love. The paper had rapid solidification and electron microscopy, two subjects in which we were interested, opened up new opportunities. But I didn't realize at that point of time how wonderful a world has been opened up for us by Danny. It's not only exciting, but also beautiful. So thank you, Danny, for giving me 25 years of a life where I could live with these wonderful objects that you first created, and then we could expand on them. I thought I could go down memory lane the last 25 years. Not just my work, the work of colleagues. As Danny in his introductory remarks said, I also represent the Indian quasicrystal community and also a little bit of the Asian community as well. As you'll see here, my quasicrystal work was done mainly in the Indian Institute of Science. But I'm also attached to the National Institute of Advanced Studies, where I am working in the School of Humanities. So I have great interest now in science and humanities, if you like. And one of the things that interested me first was the history of the Indian Institute of Science, where we recently completed 100 years. Then I thought I'll turn my attention to the history of quasicrystals, the discovery of quasicrystals, when I saw Professor Hargitai, I think, is talking later this evening on the discovery of quasicrystals, various things that have happened. So I thought it would be interesting to look at it. And this morning, I was actually interested in the comment made by the president of Technion, saying, how do you identify gifted individuals? How do you nurture them? How do you make science grow? I think even more important for a country like India, we must know how to create creative scientists. And one way is to look at how discoveries have been made, what all they contain. So I'm going to talk a little bit about all this in the course of this talk. And in particular, in a country like India, at the beginning, not anymore so, we didn't have to have all the equipment, we did not have all the knowledge, yet we could make some discoveries. So I would like to narrate some of that. So now it's said, not only history of science is becoming the geography of science. The focus of science is moving, if you like, towards East. Israel, I include Israel now in the Asian community very strongly because I'm speaking right here. India, China, Japan, Korea, they're all emerging in science. I mean, every day if you look at the newspapers, you find what the emerging economies of India and China are doing, what the emerging scientific countries like Japan and Korea and Israel are doing. So it's interesting to look at it. And I think this almost coincides with the quasicrystal revolution. If you look at years before 1985, you may not talk about India in such sense, but this work on quasicrystals gave us a visibility and authority. We could hold conferences, we could invite people, we are taken seriously and so on. For that also, Danny, I'm very grateful to you. So I'd like to also draw some attention to Indian contribution to number theory. It may not go back 200 million years, as Walter said, but certainly goes back almost 2,000 years. So some of those aspects I'd like to touch upon. Tilings in Asia, I think they're very fond of tilings, so I'll come to that. But history begins in April 1982 with Danny's work. And then there were some premonitions in India in 1978. I'd like to show how this was not seized upon. They did look at 5-fold and 10-fold crystals, 10-fold symmetry patterns, but didn't realize. Danny did that. You know, it was essentially, in his case, a serendipitous discovery. He was looking for a strong aluminum manganese alloy, but didn't dismiss the odd-looking 10-fold pattern, but pursued it with great tenacity. And I would like to also emphasize the fact that many of the new quasicrystals have been mainly discovered in India, China, and Japan, so I like to draw attention to that. So it's not a parochial, chauvinistic show, but just to look at how science has grown in this part of the world now in the last 25 years. I didn't realize John Mary was going to use this. Of course, it's his rightful photograph because he took that photograph, and the mystery of that is already done. So it's a wonderful occasion for me, I must say that, because there is Professor Ko, a very dear friend, and myself, and Nathan, and Dan Shechtman. And the important point is two of us represent, if you like, more than half of humanity. And that was represented in that particular dinner we had in that quasicrystal meeting. I may also add here, and this has been referred to, that with Danny, I first, as I said, met him in print in 1985, but we met actually in the Beijing conference organized by Professor Ko. There was a little problem of a visa, but that problem was overcome, and then we met in Xi'an, and ever since then we have become very close friends. Especially when we learned that we have the same supervisor, Professor David Brandon, and also the fact that we share the same birthday. I put down the papers written by the individuals shown in the previous picture. I call them seminal papers. This is the beginning, if you like, of the story 25 years ago. But coming to the close packing of spheres to which Marjorie Senecal referred, the Kepler conjecture which was proved by Hales, he refers in his thesis to the first problem solving in this area by Aryabhatta, an Indian astronomer who lived almost 2,000 years ago. So it's very interesting that a modern problem was originally thought of in the Indian scene by astronomers as to how spheres can be packed together. I thought that's interesting. And I think it's also important to note that Fibonacci numbers, which rule our entire quasicrystal field, if you like, in the West, the sequence was studied by Leonardo of Pisa, known as Fibonacci in his Liber Abaci in the year 12,002. But long before that, Indians had given, of course, those numbers, 0 and 1, and that is how Leonardo could learn how to add those numbers. 1 and 2 is 3, 3 and 2 is 5, and if he didn't have that Hindu, which I may call now in this place Hindu-Arabic numerals, there had great difficulties in adding the Roman numerals. So he could add them very readily and come across sequence. But long before that, it appeared under the name Matra Meru, Mountain of Cadence, in the work of the Sanskrit grammarian Pingala in the year 200 BC. So it has a long history in India. And I don't want to go through the whole thing, but merely state the last one, the Gayatri Mantra. This is something I chanted when I became a Brahmin at the age of 7, contains the string Savi Thur Navarenam, in which Thur and Ren are long or Guru, the others being short or Lagu. So this was built in, the long and short sequence. What we consider to be making our quasicrystal is there. I didn't realize that I had been singing quasicrystal in prosody right from the age of 7. Now, the other thing here, I'm on a slightly more doubtful ground. I had a discussion with Marjorie. Recently, I came across the work of Yves Mayer. I had not known about his work earlier. He had come to India to receive the Gauss Prize for Applied Mathematics in the year 2010 on the International Congress of Mathematics. Then he was re-interviewed, and then he states in his interview that the Mayer sets were discovered by him in 1969, and in a way, it determines whether a structure generated by substitution as long-range order is an algebraic property of the matrix which describes the substitution. The generated structure contains Bragg peaks in the Fourier spectrum. Only the largest eigenvalue of the substitution matrix is the so-called Piso-Vijay-Raghavan number. I heard about the Piso number, of course, from Ludwig Danzer long back, but I didn't realize that Vijay-Raghavan's name also was attached to that. Vijay-Raghavan is a famous mathematician along the lines of Ramanujan, Srinivasa Ramanujan, and other number theorists. So it's interesting to look at it, but it appears now that Mayer didn't recognize the significance of his work at that time, that it had connections with Penrose tiling, with the quasicrystalline order, and so on and so forth. But much later. I think this is part of the nature of scientific discovery. Sometimes we discover, we don't know what we have discovered. Little later we are able to understand that and say, look, I did this before. And I think who made that statement? No discovery is made for the first time. So this kind of thing happens all the time. It's well known now, thanks to Steinhardt and Liu, that the tilings patterns in Iran and elsewhere show quasi-periodic tilings. Of course, all of us are familiar with the Alhambra tilings. And as I was searching for this lecture about Indian connections and so on, I came across in one of those papers, even in Agra, in the famous Taj Mahal, a similar quasi-periodic tiling appears. Now I hope to go back and look at it and study it in more detail. So you can see the intimations, if you like, of an order, a periodic order, if I may say so, or quasi-crystalline order exists in the Indian scene and in the Middle Eastern scene. Now, also it's true that three-dimensional tilings of the type that Penrose started with the two-dimensional tiling have been explored by Miyazaki in Japan. This is a wonderful opportunity for me to meet a mathematician. He was not very fluent in English. He has written many books, looked at many structures and so on, and pictured them very beautifully. So later, with Eric Claude, my colleague in India, we worked the 3D tilings, as it were, whereby overlapping of the two tilings, you can create the Penrose type of tiling. So this is the current science title, where all 4 types of tilings, which are originally thought of by Steinhardt, could be pictured by us. Now I must come to the 1982, the aluminum manganese phase diagram. I think Danny took to it not because he was looking for quasicrystals, he was just looking for a stronger aluminum alloy. He wanted to put 14% aluminum into aluminum solid solution and quenched it. And what he got, of course, is well known. A paradigm shift occurs in 1982 by his colleagues, and I'm very happy to see that Denny is with us on this occasion, 1984. But the main thing, as has been narrated before, I think this is very important for all of us to bear, that when you find something like that, even if there's a skepticism or doubt and whatnot, to carry on regardless, to be tenacious about it. I think that's a remarkable trait, and we do salute Danny for not giving up. It could have been very easy to give up publish one paper with these pictures and move on to the next thing. But instead, you pursued this dream and went on to create a whole new world for us. When we did, this is a picture which we took early in 1985 because the patterns, the alloys could be readily melt spun, aluminum alloys to begin with. And also we produced some of the early electron micrographs. At that time, we didn't even know that these pictures could be got, because we didn't know what quasicrystals were. We could get wonderful electron diffraction patterns. So some of the earliest electron micrographs were produced by us. But we didn't pursue that further. I mean, in principle, if we had wonderful instruments, we could have done very much more work. But some of the early micrographs were actually produced by us. And I must say here, in the Indian scene, there was also a lot of support for this type of idea. This is Professor Ramaseshan, who was the president of the Indian Academy of Sciences. In 1985, March 11th, 1925, please note the date, his president's address was a new concept in the architecture of solids. He was talking about quasicrystals. So you can see the country was excited about this. I mean, November 84 to March 85 is not a far-off thing. And Professor Ramaseshan was not working in quasicrystals. He has not done work in quasicrystals, but was a crystallographer, was a nephew of Sir C.V. Raman. So he's very much interested in crystals. When he saw something like a crystal, but having different types of diffraction patterns and so on, he was very much attracted to that and made it the subject of his personal address, which meant it gave us a lot of strength. The president of the Academy of Sciences thinks that there are quasicrystals, then it becomes very easy for us to work and get additional credit. I must say here, that when we started the work in January 1985, we had a transparent electron microscope. We had already done a lot of work on rapid solidification. And as Pasteur said long ago, chance favors the prepared mind. So we are ready to work on this. But this paper was ignited us. I mean, I cannot really fully put across that excitement that seized us at that particular moment. So we went on. And the very first work before that was done actually in Benares. This was done by Shastri Suryanarayana, along with collaboration with colleagues from Belgium, Van Sande and Van Tenderloop, but it's published in Material Research Bulletin in 1978. But you'll notice the title of the paper contains something, a new ordered phase in the aluminum palladium system. They didn't say a new intermetallic or a new phase, a new ordered phase in the aluminum palladium system. They saw the tenfold diffraction patterns, but assumed, as many other people would have done, that these are all due to twins. So this was dismissed by them. A great opportunity was lost by India in the sense that if they had pursued it more vigorously, they could have done much more work. So this is a lesson that I tell my Indian colleagues, that don't overlook this. Look at other possibilities, other opportunities, and so on. And I'll come back to Van Tenderloop a little later. And in the same paper, they had also looked at aluminum manganese nickel alloys, on which a lot of work on quasicrystals, rational process has been done much later. So you can see the pattern, you can see the quasi-periodic nature, the periodic nature, all that is there. But this was missed. I mean, it's a great miss for Indian science, if you like. But it had to happen because we are not fully prepared. Now, when we started our work, electron microscope quasicrystal and rapidly solidified aluminum 14% manganese alloy, we found the decagonal phase. It's quite a remarkable thing. The second paper in Current Science shows these patterns, electron microscope quasicrystal and related structures. You'll notice two things. The first paper was published by some Scripta Metal. It attracted immediate attention. Professor Schumann, who was editor of Scripta Met, had come to India at that time, looked at our work and said, why don't you publish in Scripta Met? We did that. Current Science was, the editor was Professor Ramaseshan. He was very keen that papers of high quality should be published in an Indian journal. So he persuaded us to publish in Current Science. We did that. I don't regret it now, because it did give us a lot of visibility, if you like, in the Indian scene. It's also cited. I mean, I must thank the quasicrystal community that this paper, in which we reported first the two-dimensional quasi-periodicity and one-dimensional periodicity, electron microscope quasicrystal and related structures, is very well recognized. I'm showing it over here. We could assemble all the patterns together, and that is the tenfold pattern, the two-fold patterns perpendicular to that, and put it together. But much to my regret now, at that time we didn't quite recognize that the pattern which is perpendicular to that is a tenfold pattern. That's a decagonal phase. We could recognize it's a two-dimensional quasicrystal. There's a quasi-periodic layer. There is something perpendicular to that. But we didn't quite put it as a decagonal phase, a tenfold phase. So we did discover the two-dimensional quasicrystal, but not the decagonal crystal. In the paper in Scripta Metallurgica also, it's not a picture from that, we showed that the quasicrystals occur in a faceted way, morphologically. Again, we should have recognized that discovery. It's an important discovery because crystals are known to have a good morphology. Quasicrystals also have morphology, but at that time we didn't realize there could be a question as to whether quasicrystals also could have well-faceted substances, objects, and so on. We just put the picture in. And much later, of course, he realized that the point symmetry is represented, the dodecagonal symmetry is represented there. And Osawa, who worked on the fullerene, the C60 stability long ago, missed out, of course, on the discovery of the fullerene itself. Later was asked, what are the secrets for discovering something? He said, when you make a discovery, you must recognize that you made a discovery. Give it a good name, like Buckminster fullerene, and publish it in Nature. So, like that, I felt that while we could see these patterns, we could see the morphology of the quasicrystal, we didn't jump and say, look, we have found something very interesting, something very fine, that just like crystals, quasicrystals also grow in a faceted form and could give rise to these wonderful shapes. This is not from our work, but it was inspired by the work that we have done. In the electron microscopy work that we did, we found an icosahedral quasicrystal and decanal quasicrystal coexisting with an orientation relationship between the two. This is from Hiraga's work. The 5-fold axis is parallel to the 10-fold axis. It's very important that the quasicrystals are so closely related. Again, the whole question of an interface between a quasicrystal of a different type, a 2-dimensional quasicrystal and 3-dimensional quasicrystal, was explored in that, but not emphasized. This is from Louis Bendersky, who is also a student of Technion, a close colleague of Dan Schechtman, and he put together the same patterns that we had obtained, similar to that, independently, and used convergent beam electron diffraction to show that's true 10-fold symmetry, and he called it decanal phase. So it's one of those things where the same material was looked at by two different groups, and Leo was able to spot on, find out that it's actually a 10-fold symmetry and called it a decanal phase. But I'm very happy to share this credit with him. I go back to the work of Van Tenderloh and Amelix, who had worked with the Benares group on aluminum manganese nickel alloys. I said these must contain quasicrystals. I traveled to Belgium once and said, look, do you have those samples? They had the samples, they had the patterns, and we produced a major paper in the Journal of Microscopy on quasicrystal and the crystalline homologs in aluminum manganese nickel alloys. It's a very important thing because rational approximation was just beginning to be recognized, and we could get extraordinary patterns, both in terms of electron diffraction and the micrographs, and it's a privilege to have collaborated with Professor Amelix, Professor Van Tenderloh, and Van Danwyk. Now, the same group had earlier done work on what is called tau phases. It's an interesting story. In 1957, Lu and Cheng took the nickel aluminum alloys, to which some aluminum nickel copper alloys, made it into aluminum nickel copper alloys. Then they found they got a variety of phases, not just the ordinary B2 phase, but longer order phases. They call them tau. I mean, it's very interesting. I mean, tau is, of course, associated with the golden mean. Without knowing the significance of that, they called it tau phase. They did only X-ray diffraction. And as Marjorie Senecal said this morning, quasicrystals want visualization. When you're able to see the patterns and the symmetry, then it triggers something in you. So in 1978, Van Tenderloh and Amelix produced these patterns. Tau 2, Tau 3, Tau 5, Tau 8, and Tau 13. In Tau 2, that basic reciprocal vector is divided into two parts. In Tau 3 into 3 into 5, 8, 13. They just reported like that. Because at that time, the idea of quasicrystals, the idea of the Fibonacci numbers had not sunk in. So when we started work in 1984, 85, 87, we said these are the same as the one-dimensional quasicrystals. This is an important work that we have done from the Indian scene, that by just looking at this pattern, we didn't produce this pattern, we looked at this pattern. We said these are just like we have a 3-dimensional icosahedral quasicrystal, a 2-dimensional decanal phase, we have a 1-dimensional quasicrystal. And we did, this shows the same pattern in terms of schematic form, 2, 3, 5, 8, etc., published in Acta Metallurgica in 1987. Then we went on to look at these phases and show there is a correspondence in terms of the lattice parameter based with the Frank's ratio. Frank, as you might remember or recall, projected from a 4-dimensional cube to get a hexagonal phase, but it had a particular axial ratio. So in terms of that Frank's axial ratio, we have now, that is RF. If you divide by 3, you get that. If you multiply by 2 and divide by 3, you get that. So the whole series of tau phases are related to the Frank's ratio. So we are deriving, if you like, a 4-dimensional cubic crystal, all these phases with different axial parameters. Now the question of Pauling's twins was raised by Walter this morning, and later Professor John Kahn and Leo Bendersky produced those twins, which was visualized by Pauling, possibly. But the interesting point is these are irrational twins. These are from aluminum manganese silicon alloy. These are pictures are from there. You can see that there are 3 crystals. They are crystals, but they are twinned by a 72-degree rotation around 1000, the 5-fold axis of an icosahedron. The crystal itself doesn't contain that. It contains only the motif. But if you rotate around that motif, you can get 5 of them. So you get, if you like, the 5-fold pattern, the 3-fold pattern, and the 2-fold pattern. So we were able to show that such twinning can occur and can be interpreted in terms of coincidence-wide lattices. This is something I have talked about in the last time I was here in Technion, that if you get a twin with an index of 3 coincidence-wide lattices to which Wayne Kaplan made a reference, it is twinned around 211 by 180 degrees, and if you call it the stacking sequence, it has a unit called B. If you twin it around 3-2-1 axis, then you get 1 in 7, and we call it A. By mixing these two units, A, B, just as like we do the Fibonacci sequence, we get the next one as 532. You can see the indexes add up to that. We get 1 in 19 as the coincidence points, and its the sequence is AB, AB, AB. So we can go on to 49, 129, 337, and of course right up to infinity. So we are able to demonstrate that the coincidence-wide lattice concept holds good even for these irrational twins, that we can regard them as a series of Fibonacci units which are put together. Now I come to the Indian discovery of quasicrystals, the Chinese discovery, and the Japanese discovery of quasicrystals. I want to pay a very special tribute to a dear friend of mine who unfortunately is no more with us, Ramchandra Rao. In 1985, he was working at Benares. I told you that they missed an important discovery in 1978. And Ramchandra Rao was working in Benares while I had moved to Bangalore, and I thought I had scored a triumph over him because we could immediately get our first paper out in April 1985. But on his own, he worked on a completely different system, namely the magnesium zinc aluminum system. And what I appreciate about him, for an Indian scientist, this is indeed extraordinary achievement. If you look at the paper again was published in Indian journal, Pramana, Indian Journal of Science, Physics Science. It's called A Basis for the Synthesis of Quasicrystals. It was received on July 1st, 1985. You must go back to 1985, just a few months after the original discovery. We didn't quite know what quasicrystals are, what to do with them. Do they have ordered arrangement or disordered arrangement? What are they like, etc. And here is our friend giving the title, A Basis for the Synthesis of Quasicrystals. Many of us worked on aluminum systems because Danny showed that aluminum manganese alloys do that, so you change the percentage, 10%, 15%, 20%. World over, many people are working. And here, Ramchandra went on a completely different track and took magnesium zinc aluminum alloys, and he shows the patterns. And shows the patterns he's applying, showing that you can get an icosahedral quasicrystal. And of course, what he took was the Pauling compound, the Bergman compound, the building of the Bergman cluster. He saw this picture in a Russian edition and saw that since it contains icosahedral clusters, if you cool such an alloy very rapidly, you should get quasicrystals. I think this is one of the best papers that has come out of India, to think completely differently. He was isolated in Benares. He was not reading all the papers that were appearing, but yet could sense immediately as he saw that. And this could form the basis for the sense of quasicrystals. All of us know now that quasicrystals have rational approximant, so structures which contain such structures are prime candidates for producing quasicrystals. But to think that 25 years ago, 26 years ago almost, somebody could fathom that and do that, I think is an extraordinary achievement. In a similar way, in fact, at the same time that Danny was exploring this, Professor Kuo was also looking at 5-fold symmetry in many of the phases. Frank Casper phases and so on. There was a reference to in Walter's thing about sigma phase, mu phase and so on. He was studying all the topologically closed packed phases and so on, and saw very often you can get 5-fold symmetry. And more importantly, he went on to work on titanium-based quasicrystals. Titanium 66, iron 33 in 1986, and then Kelton followed it up a little later with titanium cobalt. So this opened up a completely new field of titanium-based quasicrystals, when everybody again was working on aluminum quasicrystals. So you can see Ramchandra Rao paved the path for magnesium zinc aluminum alloys, if you like, and Professor Kuo paved the way for titanium-based quasicrystals. And of course, I'm glad that Anfang Sai is here. I call it the Anfang Sai way, back to the future, an account of the discovery of stable quasicrystal. He's going to talk about it. In fact, he asked me, am I going to say anything about human authority? I said, no, except to show one slide and pay him also a tribute, human authority rules, and look for unidentified phases in the phase diagrams. By using these two rules, he discovered a very large number, aluminum, copper, iron, aluminum, cobalt, aluminum, palladium, manganese, and also zinc, magnesium, rare earths. Not zinc, magnesium, aluminum, but going to rare earths, and cadmium, magnesium, rare earth, cadmium, ytterbium. And rightfully, he was given the Jean-Marie Dubos Award in ICQ 9 at 2005. You can see how from one group, by having an intuitive way of going about discovering of these quasicrystals, he enriched the field, expanded the field so much. I put down this classification of quasicrystals. Originally, one would have thought that aluminum manganese is an aluminum alloy, magnesium 36, zinc aluminum alloy would be a magnesium alloy, and so on and so forth. Also given the names of the people who discovered this. In fact, in 1985, we did the first work on a quaternary quasicrystal, magnesium, zinc, aluminum, copper, along with Mukhopadhyay. The majority component is aluminum, but the large atom is magnesium. So I'll come to it in a minute. Then I already referred to the titanium vanadium nickel by Kuo in 1985, and by Odier in 1986 of aluminum lithium copper, and Luo in the zinc magnesium rare earth, and then of course Professor Inouye in the hafnium alloy, Sai's work I already referred to, and similarly Ishimasa found a number of quasicrystals. So if you look at the many systems, very many systems, especially in that period where I have given from 1984 to almost 2001, many of them were found by Asian scientists working on this. It's quite an interesting thing. But what I want to say is, having looked at it, we try to work on this, that the general tendency of metallurgical theory would be to look at the majority component, because you have a base, to that you add other components and you look at it. But we felt in these quasicrystals, where sphere plays an important role, you have to look at what is the largest atom. So what I have given here is the largest atom. If you look at them, it falls into a few classes. For example, aluminum and gallium, which will belong to the same thing, and titanium, zirconium, hafnium, which will belong to the same thing, and rare earth, ytterbium, scandium will come to the same size, and of course magnesium. So we looked at it that in classifying quasicrystals, we shouldn't go by what is the majority component, but look at what is the largest atom. It's very easy to arrive at the stoichiometry of this, how these are stacked together. So basically, what I like to submit, which we have written about in this paper, is there are 4 types of quasicrystals. And you will see, I'm not talking here about atoms. I'm talking about large and small atoms. That means all the quasicrystals are either binary or pseudo-binary. You can add a third or a fourth element which is very similar to that. So even the question of order becomes easy to understand, because if you had aluminum and gallium, for example, they'll substitute for each other. It is not necessary that they should fit into the same spot in the same way, but certainly they do that. So we have put together here that all quasicrystals can be considered as pseudo-binary intermetallic. Unfortunately, for the magnesium zinc aluminum class, we don't have an existing material. But for the Mackay class, we have aluminum manganese, Kuo class, we have titanium nickel, and the Sai class, which he discovered, a binary cadmium ytterbium and cadmium calcium. Now, we can replace nickel by zirconium and nickel, hafnium and nickel, so it's possible to build a ternary, quaternary, and even a quinary alloy. But basically, as far as the structure of these 4 types of quasicrystals are concerned, they are the same in each one of them. That is, Bergman class, they will have the same structure. In the Mackay class, they have the same structure. And you find that magnesium and lithium can substitute for each other. So you have, if you like, lithium and magnesium and zinc aluminum. Lithium and magnesium are the large atoms, very different in terms of the electronic characteristics. Yet here, the size factor seems to play an important role. So I think it's a very important contribution, I feel, from our side, that we can understand all the quasicrystal structures as being either binary or pseudo-binary intermetallic. We have gone on further to show that if you want to produce a glass, you have to go for a ternary or a pseudo-ternary alloy. That is, a crystal structure is able to sustain, if you like, 2 types of different types of atoms. But if you put a third one, which cannot fit into this category, then of course the crystal or the quasicrystal structure is destabilized and you result in a glass. Here, I think Professor Kelton might touch upon some of that. The glasses and quasicrystals are closely related to each other. The icosahedral order that Danny found in quasicrystals, and also I think he was looking for amorphous alloys which also have icosahedral. It's a permeating theme. And in this, a lot of work has been done. I'm relating, it's not a complete list. In the hafnium copper silver, we have published, and we find there is a close comparison with the glass and quasicrystal forming ability, and zirconium alloys, and also titanium alloys, we find that. So the multi-component alloys viewed as a pseudo lower order alloys. So if you have a pseudo ternary alloy, it's a glass. If you have a pseudo binary alloy, it's a quasicrystal, has been borne true by this. Here it shows, for example, from an alloy, zirconium gold platinum, which became amorphous, but by heating it, we are able to produce small quasicrystals in that. So the field opened up by Danny nearly 26 years ago has expanded in many directions. It has brought a link between crystals, quasicrystals and glasses, allows us to explore in many systems how it happens, and has been demonstrated. I have not worked too much on properties, but the talks this morning by Janus Dolinsek and Professor Jean-Marie Dubois just now showed that there is an equally wonderful opportunity to explore the properties of all these materials. More than all this, it has been a great privilege to collaborate with a large number of people. This field lent itself that well. My main collaborator has been Kamanyo Chattopadhyay, and we worked together with Subarna, Tangaraj, Mukhopadhyay, Alok Singh, Anand Swarni, Jaisira Basu, Divakar, all got their PhDs. It lent itself beautifully to, if you like, doctoral investigations of various types. And we have collaborated with Kuo, Professor Innovate, Professor Dong, Alan Mackay, and Eric Lord. And I must pay a particular tribute to Alan Mackay because he has been an inspiration for us. I didn't quite know until 20 years ago or so of his beautiful work where he produced the first optical diffraction pattern for the Penrose styling. Now it is coming into full recognition, as it were. At the time he did it, he thought it's great fun to play with. Of course, I mean, there's a danger in playing, having fun only. You know, you must realize that it's a very significant, important thing. And of course, Danny himself, John Kahn, Leo Bendersky, Van Tendalu, Ken Kelton, Urban, Episai. I am co-authoring many papers with these people here, very wonderful. And also my colleagues Banerjee and Gautam Kumar Dey. We did a lot of work on octagonal quasicrystals. I'm not reporting it here. And my late colleague and dear colleague, Professor P. Ramchandra Rao. So Danny, it gives me great pleasure to wish you happy 70th birthday. It's a few days from now. But above all, I want you to thank for enriching all our lives with your discovery. A discovery very important, very significant, and also very beautiful. It's not often that it happens that a beautiful and significant discovery coincide together. So let me salute you, not just on my behalf, on behalf of the Indian quasicrystal community, and I may go further to say on behalf of 1 billion Indians. Thank you, Dan.